Hello everyone, Namaskar, welcome to Maths Guidance and welcome to the third lecture of chapter number 10, that is circles. So far we have discussed three theorems in the last lecture, lecture number 2. The first one was that equal chords of a circle subtend equal angles at the center. Okay. The second one was the converse of this theorem, that if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. So these two theorems we have seen and its proof also. The third one was the perpendicular from the center to a chord actually bisects the chord. So these three we have studied. Now let's continue this learning. Let's come to some other properties of the circle in the third lecture. So let's start the video and please watch my videos till the end. Thank you very much. So friends, let's come to this topic, circle through 3 points. And in this under this topic, basically we will learn that how many points are necessary to determine a circle, to draw a circle. Okay, so we have studied in the chapter lines and angles that 2 points are necessary for drawing a line or line segment. Okay, we have studied in that chapter that there is only one line passing through two given points. Let us suppose these are 2 points. This is the unique line passing through these 2 points. All right. Now similarly we can write it that there is only one line passing through, there is a unique line, you can say there is a unique line passing through 2 given points, unique line passing through 2 given points, passing through 2 given points. All right. Similarly, let us check that how many points are needed for a circle. Let us suppose we have been given 1 point. Okay, so we can draw circles like this. So basically we can draw infinite number of circles from 1 point. If we have been given 1 point, so we can draw infinite number of circles, infinite number of circles. Okay, suppose we have been given 2 points like this, 2 points, then also you can see you can draw infinite number of circles. Okay, if you have been given 2 points, then also infinite number of circles you can draw. Now the case comes that you have been given 3 points. Now 3 points we can choose in 2 ways. 3 points, one is that all the 3 points are collinear. This is one of the cases. Second one, 3 points are non-collinear. Okay, so if the 3 points are collinear, let us suppose like this, 1 2 3, then what happens? Then if you cover these 2 points, then you can draw a circle like this. Now if you cover these 2 points, then you can draw a circle like this. So basically 1 point either lies inside the circle or outside the circle. If the points are collinear, then one point either lies inside the circle or outside the circle. That is, it cannot cover all 3 points. The circle cannot cover all 3 points. This is the scenario with collinear points. But if the 3 points are non-collinear, okay, if the 3 points are non-collinear like this, in this case we can draw a circle like this. Okay, so these 3 points are non-collinear. Non-collinear means not in a line, not collinear. Okay, that is called non-collinear, not in a line. Okay, not in the same line. So basically this is the scenario where we can draw a circle. So 3 non-collinear points are needed for drawing a circle. All right. So there is only one circle passing through 3 given non-collinear points. The statement is like this: there is only one circle, one and only one circle. Okay. Now actually this is the theorem, that there is one and only one circle passing through three given non-collinear points. Now we will see its proof. Let's do it. First understand these things, that if 2 points are given, then there is a unique line passing through these two given points. Alright. Now if 1 point is given, we can draw infinite number of circles. If 2 points are given, we can draw infinite number of circles again. But if 3 points are given, but all the 3 points are collinear, then you cannot draw a circle covering all the 3 points. So 1 point will either lie inside the circle or outside the circle. You can say it interior of the circle or exterior of the circle. So we need 3 non-collinear points to draw the circle. Okay, this is our agenda, that there is one and only one circle passing through 3 given non-collinear points. Okay, so let's see it. Let's see the theorem and let's prove the theorem. Alright. So friends, this is the theorem, that there is one and only one circle passing through 3 given non-collinear points, and we are going to prove it. Okay, so let's see the proof. It's a simple proof. Suppose we have been given 3 points like this. One is here, one is here, and one is here. Okay, the 3 points are, let us suppose, A, B and C. Okay, and let's join these 3 points like this, A, B and B, C. Okay, now what we will do, that we will do one construction. Okay, so given is only 3 points, 3 non-collinear points. Given is A, B and C are 3 non-collinear points. All right. What we need to prove? To prove that there is a unique circle passing through these points. There is a unique circle passing through these points. Okay, we will do one construction. And what is the construction? The construction is, let us draw the perpendicular bisectors of this AB and BC. Okay, like this. Suppose you draw the perpendicular bisector, it will come like this, and it will intersect at some point. Let us suppose this is O. Okay, so what we will do, what we will construct, draw the perpendicular bisectors. Draw the perpendicular bisectors of AB and BC. Okay, intersecting at point O. All right. Now let us do the proof. Since O lies on the perpendicular bisector of AB, since O lies on the perpendicular bisector of AB, therefore OA is equal to OB, because every point on the perpendicular bisectors of a line segment is basically equidistant from its endpoints. All right, every point on this perpendicular bisector. Suppose we take here, then this point, this distance and this length will also be equal. Suppose the point we take here, then it is also equal. So every point, let us write it, every point on the perpendicular bisector, of a line segment, is equidistant from its endpoints. We know this thing. Now similarly we can write that OB equal to OC. Since O lies on the perpendicular bisector of BC also. O lies on the perpendicular bisector of BC also. Okay. Now OA equal to OB and OB equal to OC. Now we can say that OA is equal to OB is equal to OC, which means that these 3 points A, B and C are equidistant from this point O. OA equal to, let us suppose you join like this, OA, OB and OC. That means what? That means what? The points A, B and C are equidistant from the point O. That means A, B and C are equidistant or at equal distances from the point O. From the point O. So if you draw a circle with center O, if you draw a circle with this center O and radius OA, OB, OC, you find that you can draw like this. Okay, and that will be the unique circle passing through all these 3 points. The circle passing through the points A, B and C. When you draw the, if you draw the circle having center O and radius OA or OB or OC. So this is the unique circle. This is the unique circle passing through all these 3 points. Unique circle passing through all the 3 points. All the 3 points A, B and C. And this is what we have to prove. So this is proved now. Alright. Okay. Let us see again it. There is one and only one circle passing through 3 given non-collinear points. Let us take A, B and C 3 points. We will construct the perpendicular bisector. It will intersect at O. Now OA equal to OB and OB equal to OC. So OA equal to OB equal to OC. When we draw a circle from center O, this is the unique circle passing through these 3 points A, B and C. Alright. It was a simple proof. Okay, now let's move on. So friends, let's come to a new topic. Its name is equal chords and their distances from the center. Okay, and we are going to see one theorem also, that equal chords of a circle are equidistant from the center. But before going to the theorem directly, let's understand one thing, that what is the distance of a line from the point. Let us write it, distance of a line from a point. So basically, let us suppose this is a line. Okay, let us suppose this is A, B, and here there is a point, let us name it P. So the distance of this line from this point P is the least distance, that is the perpendicular distance. Okay, because there are so many points in this line, here also, here also, here also, here also. So what is exactly the distance of this line from this point P? So basically this is the perpendicular distance. It is called the perpendicular distance, and we write it like this: the length of the perpendicular, from a point to a line is called the distance of a point from a line. Distance of the line from the point. Okay, so it was necessary to go directly to the topic or the theorem. So basically this perpendicular distance is the distance of a line from a point P. Alright, the length of the perpendicular from a point to the line. Now let's come to the theorem which we are going to study. the theorem is, since we are studying circle, so the theorem is equal chords of a circle are equidistant from the center. Theorem is equal chords of a circle, or we can also write here or of congruent circles. Okay, equal chords of a circle or of congruent circles are equidistant from the center or centers, because we are dealing with this also. Okay, equal chords of a circle are equidistant from the center. So this is the theorem, and we are going to see its proof. Let's do the proof. Let us suppose this is the circle and these two are equal chords. Let us suppose this is AB, this is CD, this is the center. Okay, now let us, you can join this also, OA, OB and OC, OD, you can join like this. Now let us see, if you draw the perpendicular bisector like here and here, okay, and let us name it L and M. So given is a circle with center O, okay, and this chord AB equal to CD. So basically let us write it AB equal to CD. The chords are equal. This is the main thing we have been given. Also OL perpendicular to AB and OM perpendicular to CD. Okay, now we have to prove that this length is equal. Which length? OL is equal to OM. Okay, now we have joined these things, OB, OA, OB, OC and OD. Now we know that this perpendicular bisector, basically this perpendicular bisects the chord. Okay, so we can write that, let us see the proof. We can directly write that AL equal to half of AB. This perpendicular bisects the chord. We have studied in the in our earlier lecture or in the other earlier topic. Okay, so AL equal to half of AB, and also CD equal to, sorry, CM equal to, let us write CL equal to half of CD. Now we have AB equal to CD. This means what? AB equal to CD. This implies AL equal to CM. We can say AL equal to CM. Okay, now we will compare these two triangles OAL and OCM. So in triangles OAL and OCM, these are the two right triangles. Okay, we have AL equal to CM. This has been proved here. We have OA equal to OC. This is the radii. Okay, and the third one is the angle 90 degree. Angle OLA equal to angle OMC 90 degree. Therefore by RHS we can say that triangle OAL is congruent to triangle OCM, and therefore we can say that this OL equal to OM by CPCT, OL equal to OM by CPCT. Now it is proved. So we have seen that equal chords of a circle or of congruent circles are equidistant from the center or centers. Given these two chords AB and CD, and these two are equal, AB and CD, this is the perpendicular OL to AB and OM to CD. Alright. Now we have to prove that OL equal to OM. Equidistant from the center. OL equal to OM. So AL equal to half of AB. We can directly draw AL equal to half of AB. CM equal to half of CD. We know that because the perpendicular from the center to the chord actually bisects the chord. Now in triangles OAL and OCM, we have seen that these are the two right triangles and we have proved that these two are congruent. So from simplicity we can say that these two lengths OL and OM are equal. Alright. Now let's move on. So friends, this was the lecture number 3. We have seen 3 theorems. The first one was that there is one and only one unique circle passing through 3 given non-collinear points, and we have seen its proof also. Then we saw one theorem that equal chords of a circle are equidistant from the center, and we have done its proof also. One is the converse of this theorem, that if the chords are equidistant from the center, then these chords are equal in length. So this concludes our lecture number 3, and in lecture number 4 we will solve some problems regarding these topics, and also we will move on to some new topic. All right. So please be connected with my videos and watch my videos till the end. Thanks for giving time to this channel. Thank you very much.